Greetings everyone, Professor Simon here, and we're going to go off on a little tangent and talk about some theory that's going to help build us up in this multivariable calculus. Okay? The multivariate chain rule is just an expansion of the chain rule that you talked about in Calculus 1, right? The chain rule from Calculus 1 you probably saw in this format, and then later on you worked with it in a format like this. And the whole idea of the chain rule originally was, how do I take derivatives when I have a composition, a function working inside of another function? And it became an important rule for you to be able to work some of the more complicated derivatives. And you probably still are using it now in some of the problems we're experiencing here. We used it in the last lecture at least 2 or 3 times. Okay? The multivariable version of this chain rule expands the chain rule beyond just a necessary rule that we can use for individual derivatives. It gives us a different concept of what a derivative can be when you have all of these multivariables acting together in your function. Okay? So, the original chain rule, df dx, could be equal to df dg times dg dx, given that g is some function that connects f directly to x, sort of like a middleman, where g could be thought of as a function inside of f, if you will, right? Sometimes you may have also used a substitution where f could just be a function of just g, and then off to the side, g is some function of x, and then you did your derivative separately. It's probably how you started learning chain rule, okay? The multivariate chain rule is very similar. Take a look at it in differential form here. The derivative of f with respect to t. Notice that's not a partial derivative here, okay? What that means is t is the only variable that is actually changing. But that's equal to the partial derivative of f with respect to x times dx dt plus the partial derivative of f with respect to y times dy dt. Do you notice that there's a mixture of partial derivatives with normal derivatives in there? Okay? And that's because f is going to be some function that is dependent on multiple variables, and it's basically doing the partials with f and y, with x and y, to give each one its own portion. Okay, so if you'll notice, this is sort of like a weighted, not a weighted average, but more like a weighted calculation. How much of the x change should I allow? How much of the y change should I allow? And it has to do with how the surface interacts with x, right? And how the surface interacts with y. What's happening here is I've got this variable t that's controlling x and y like a parametric equation, okay? And as x and y change, how does my value on the surface change? In other words, how does the output value of the function change as a result of changing t? So it's like this. Imagine you have a surface somewhere in your space, right? So you have a function, f of xy is giving you some surface. But what you also have is a parametric subset of equations that's controlling x and y. Remember, if we go parametric, most of the time what we're talking about is a curve. Okay? So I've got this curve giving me some x and y values from the domain, and that's giving me some curve on the surface. So f is still controlling, right? The surface here is the function f. F is still controlling the overall behavior with its own shape. However, the part of f that's being used is being controlled by t, not necessarily x and y, right? T is telling me a pathway in the xy plane. That's why you have dx dt and dy dt just as straight derivatives. Okay? But the functional change as it's going through the surface, how is the function value changing as t changes, is dependent on how f is related to x and y. So hence your partial derivatives are weighting the additions of these two changes. Okay? So recap, the overall change in f based on a change in t is going to be this weighted calculation addition between the x direction and the y direction, so that the change in f in the x direction and the change of f in the y direction are still being controlled by t there. Okay? And then you have your other version here. F is some function related coming from x and y, but then x and y, notice, are both functions of t. So I can actually take a derivative with respect to t if I wanted to, and it becomes this weighted calculation here. But you'll notice it looks a lot like the chain rule if you just look at one piece of it, right? I have the df dx, dx dt like that. It looks a lot like the original chain rule. Okay? Except here our function is multivariate. So I've got to have the partial derivatives from two different directions. Or if it was multivariate from three variables, then notice I could just easily add the partial of f with respect to z at times dz dt. It would be very easy to add in a third variable here, just following the same pattern. Okay? A fourth variable, a fifth variable. This is the generic format here. Okay? You add as many variables in the change of each one that you have. Okay? So here we're just talking about a two variable function, f of x and y. Let's get an example. Let's work this particular derivative two different ways. Okay? We've got the chain rule and we've got the straightforward way. The chain rule gives us an easy way, and it's the same thing in original calculus chain rule. The chain rule gives us an easier way to do a lot of these compound composite derivatives. But you could have probably, found a way to go around the chain rule most of the time. Like if you had some object to a power, you could multiply out the power and then not worry about the chain rule. But usually the long way like that is more complicated as far as having all the pieces everywhere. And the chain rule makes things simpler. And that's what I'm getting at here. I'm going to show you that there's the chain rule and then there's the other way. And most of the time the other way is just a little bit more messier, right? Okay, so take a look at this. I could actually turn this into a function of t if I wanted to, right? I could say d of x of t, y of t, which basically makes it d of t. The curve that I'm following in the domain follows this parametric equation, okay? So if I followed this parametric equation in the domain, it will give me a curve on the surface. And what I'll be doing is finding the derivative on that curve that follows the surface. Okay? So the first way, the long way here, is to just substitute in. That would be sine squared of t plus t squared plus 2 squared, like this. So notice, like I said, you can just directly substitute like that. But that's not using the chain rule. Okay, this is sort of the long way, if you will, the everything is in front of you sort of way. I don't need to use the multivariable chain rule now. I now have a function that is in one variable of t. And if I want to do the derivative with respect to t of d, right? Then I would just need to do the derivative of this. Okay? So let's go through all of the steps here. I would have to pull out the 1/2 from the square root. Let me go ahead and write it out for you. This is really to the 1/2 power, right? and then I'll still have all of those pieces, t squared plus 2 squared to the negative 1/2 times, and here's the old school chain rule, right? This is the old school one here, times this derivative is going to give me 2 sine t cosine t, an inner chain rule, right? Plus 2 t squared plus 2 to the 1 times 2t. Like that. And then, of course, you would want to rearrange this. d of capital D dt would then be 2 sine t cosine t plus 4t times t squared plus 2 over 2 times, let's see, square root, right? Because negative power is going to put it in the denominator. I've got a 1/2 power sine squared t plus t squared plus 2 squared. I could reduce a 2 out of each one also. Let's see. I've got sine t cosine t plus, and then that's going to be, I'm going to go ahead and distribute this in 2t cubed plus 4t, right? Because this will be a 2, right? 2t times t squared and a 2t times 2. And then in my denominator, I was able to reduce out the 2, so I have square root sine squared t plus t squared plus 2 squared. Okay, so I found my derivative. And yeah, there were a lot of moving parts in there, right? Okay, so let's make this a little bit easier on ourselves using the multivariate chain rule, okay? It's still based on a single variable, though. Notice it's still based on t, right? That's why I was able to do old school derivatives on this thing. But I can do it with the multivariable chain rule here in pieces if I want to, okay? So if I'm looking for a derivative with respect to t, right? I'm looking for this. Then what I need is some partial derivatives and some straightforward x and y derivatives. So over here, just kind of over on the side, I'm going to write out dx dt and dy dt, right? Just going to write those out. The dx dt here is cosine t, and dy dt here is 2t, right? Okay. Now, the function here, I'm going to do the partial derivatives of with respect to x and y, right? So let me go ahead and rewrite this. This is going to be to the 1/2 power, right? And then I'm going to start with the partial derivative with respect to x. Okay, so that's just this. Remember, leave it alone. To the negative 1/2 times 2x. That's partial of f with respect to x. Okay? Times dx dt. So that's cosine t. Plus, now partial of f with respect to y. Okay, so that's, again, I've got to do that same piece like I did before. That's going to be 1/2 x squared plus y squared to the negative 1/2 times 2y this time. I know, I'm running out of space. Wait, no, my new marker board anyway. Times 2t. Okay, that was partial of f with respect to y, and then dy dt. Now, of course, the partials here did have some old school chain rule in it already. So you can see where this one sort of had a more step back and do one piece at a time approach, whereas this one had a lot of moving pieces all at once. It actually ends up being very similar amounts of work, quote unquote, but it just depends on how you want to arrange your amounts of work at any given spot. And also it helps build us up to the multivariable with multiple variables instead of single variable. Okay, so I know it seems like maybe it's the same amount of work, and it's pretty similar. Okay, so here we go. Let's keep going with this one. I'm going to factor out the x squared plus y squared to the negative 1/2. I'm going to notice that 2 times a half is 1, right? Same thing here. The 2 times a half is a 1. And what I'm left with inside here is x cosine t plus y times 2t, so that's 2yt, like that. Right? Okay, so we're almost done here. See, this does feel a bit more organized than that. However, I do need to eventually turn it into, the same object. I need to have something strictly based on t, since this is a derivative with respect to t in the final readout here. So that's what I'm going to do now. I'm going to put this in the denominator, and I'm going to replace all of my x's and y's with the thing that they're actually equal to, right? So to do that, I'm going to have x is equal to sine t times cosine t plus 2y times t. Y is t squared plus 2, and I'm multiplying it times 2t. So I've got my 2t cubed plus 4t. And then, of course, this is all over. This thing is in the denominator. X squared plus y squared gives me that same denominator down there. It gives me the square root of sine squared t plus t squared plus 2 squared, like that. Okay, so again, notice we do end up with the same answer, like we're supposed to, because that's the derivative with respect to t. Okay, and it just depends on which way you prefer organizing your work. But the chain rule does compartmentalize it. Okay, it allows you to look at each individual direction, and it can keep it concise for a while until you need to bring in the actual substitutions for x and y with respect to t. Okay? I just want you to see what it is that we just computed, what we just found a function of. We have our surface d of xy, square root of x squared plus y squared is this cone, well, top half of a cone anyway, right? This is our surface. The parametric equation C was x is sine t and y is equal to t squared plus 2. What that is a subset of the domain. It's this set of points on this curve in the domain here. Okay? Now, of course, when you actually apply that restriction of x and y, that particular set of x and y's from the domain, you get the image of it on the surface here. So what we're talking about is this piece of the surface, just this collection of points that follows the surface as this set of points follows in the domain. As you can see, they are the exact same when I look over the top, right? So this is the curve in the domain, is just the x and y. And then when you actually plug it in and you get the subset of points, you get this curve in space. Okay? So that last function that we had, the derivative of capital D with respect to t, what's happening is as I let a point move along this curve, okay, the amount that the function f changes, in other words, the z value changes with respect to t as I move along this curve, would be that d, capital D of dt. Okay, that's what it represents for this curve. Okay, so you've seen what happens when we try to take a single variable on a multivariable surface. Just like before, what you end up with is a curve in space. It's a subset of the domain. Now, what happens if you have multiple variables inside of multiple variables? It's like a convoluted composition, right? And really, what that boils down to a lot of times, math and physics alike, is a change of coordinates some sort of way. You're trying to redefine the way that you are mapping the surface, but it's still using the entirety of the surface because you still have the same number of variables. Or it's also possible that you can switch from multiple variables to another set of multiple variables that has a different number. Okay? The examples that I have here are kind of limited in the scope of what's possible, but this is also pretty much the most common. So look, what if I have some function f of x and y, right? Just f of x and y, but I redefine x and y so that they themselves are the variables of two other variables, t and u. Okay, just some variables out there, t and u. Okay, so I've got some sort of relationship now from f into t and from f into u, or actually the other way around, right? If I change u and t, it will change the value on the surface. Okay, and what this equates to is I pick a point somewhere in the xy domain, and that point would map up to the surface, right, in the 3D space. But then what I want to do is I want to move with respect to t and u. Maybe it makes it easier to move along the surface, or maybe it's a different way of understanding how something changes on the surface, or whatever, right? People do this all the time, right? If you're moving along somewhere and then you want to go up an incline, well, your whole version of what is up can change, right? If you're on an incline, so you can change your internal coordinates. What does it mean to go up, and what does it mean to go left and right? And then that has variable effects along the surface that you're moving on. Okay, so this is sort of what's happening here. And you'll notice the chain rule looks the same, but now it's a partial derivative of f with respect to one of the new variables, or partial of f with respect to the other of the new variables. Okay, and the way that we get there is we take an f direction of x and an f direction of y and separate them out. And then x is going to change when t changes, and so is y. Y is going to be affected by changing the t variable as well. So again, it's that same kind of weighted calculation between the x and y directions. And again, if I had x, y, and z, or x, y, z, w, right, you can sit here and add more calculations, the partial of f with respect to z, the partial of z with respect to t, so on and so on and so on. I could have a function of x, y, and z that only goes to two variables, t and u. Or vice versa, I can have something that's f, x, and y that gets mapped to t, u, a, b, and c. You can go from two variables to five variables. I mean, it just depends on what you see as necessary in your situation. And this just happens to be a very common one, because a lot of the multivariable functions that we're doing are two variable inputs, and they're 3D surfaces. So then a lot of times our coordinate changes are some sort of coordinate change from the domain. Okay. However, when we're using, say, spherical, right, we're switching x, y, and z into rho, theta, phi, right? So that would be 3 variables to 3 variables, and then you would have all sorts of interesting chain rules from that as well, okay? This is not the hard set rules right here. You can add more to them. For example, if I wanted to do something in, say, spherical, I could do the partial of f with respect to rho, let's say, right? And what that would boil down to is the partial of f with respect to x times the partial of x with respect to rho plus the partial of f with respect to y times the partial of y with respect to rho plus, let me make some space here, the partial of f with respect to z times the partial of z with respect to rho. This could be one version of using this multivariable chain rule to convert from your rectangular x, y, and z into spherical, and I'm going to do the derivative of how the function changes as I change the value of rho, right? Keeping rho as my variable and then everything else constant. But I'm using the chain rule to do that because my function originally was based on x, y, and z, let's say. Okay? So again, it doesn't have to be 2 variables to 2 variables. This is just a very common structure. Okay? You can have 3 to 3 or 2 to 3 or 5 to 6 or whatever arrangements here, right? This is still 3 to 3, and I could do the partial of f with respect to theta. I could do the partial of f with respect to phi, and it would be the same setup, right? You would just change all the rows to those particular other variables. Okay? So that's just an example of what you can do with the chain rule there. Let's get an actual problem going on here. Okay, so here I've got a function g of xy, okay? Sine of pi over 21 times x squared minus y squared, okay? But let's say that we're going to switch to cylindrical coordinates, okay? Remember, cylindrical coordinates is really just z-axis with polar, right? So what am I really saying here? I'm really saying that I'm switching the domain from rectangular to polar. That's really all this is saying. If we're going to use cylindrical coordinates on a rectangular function, right? Find the partial of g with respect to r and the partial of g with respect to theta, okay? Because z is still z in cylindrical. So I'm not doing 3 to 3 here. I'm really just switching x and y into r and theta, okay? But instead of doing a lot of substituting and a lot of derivatives all at once, I'm going to use the multivariate chain rule to calculate these in a more organized fashion, okay? Let's start with what are our relationships from x and y to r and theta, right? Because I'm going to need to do a dx dr and a dy dr and a dx d theta and a dy d theta for these guys, okay? So let's start with the fact that x is going to be equal to r cosine theta and y is going to be equal to r sine theta. Those are our typical polar conversions there. And I wanted x and y, not the other way around, not the other polar conversions using r and theta as the answer, because I need dx dt, right? The partial of x with respect to t, well, in r in this case, right? Okay, so I'm going to have my partial derivatives of x with r and theta and my partial derivatives of y with respect to r and theta using these equations here, okay? So, what is the partial of g with respect to r? Okay, let's write that out. Let's write out the format that I'm going to be using here. That's going to be the partial of g with respect to x times the partial of x with respect to r plus the partial of g with respect to y times the partial of y with respect to r. Yeah? Okay. So let's see if we can squeeze all this in. The partial of g with respect to x. So I'll be doing the derivative of this thing, okay? So I'll have cosine, whoops. I don't think I'm going to be able to fit it all there. So let's go to the next line here. I'm going to have cosine of x squared minus y squared times the pi over 21. Forgot that. Pi over 21 x squared minus y squared. Okay, then I'm doing the inside derivative with respect to x only. So I'm going to have the 2x and pi over 21 there. So I have 2x pi over 21 times dx dr, right? So partial of x with respect to r is just cosine theta, right? Because I'm just doing derivative here of the r, and then the cosine theta is along for the ride. Plus, I would be doing the partial of g with respect to y. It's going to be very similar to this one, but what? The derivative of the y piece inside has the minus, okay? So I'll have negative 2y pi over 21 cosine of pi over 21 x squared minus y squared times the partial of y with respect to r, sine theta, like so. Okay? All right, I'm going to make a little room here. We'll come back to that one. Okay, so let's clean this up a little bit. I'm going to factor out the pieces that they have in common here. The cosine portion, the 2 pi over 21 and the 2 pi over 21 here, right? So I've got 2 pi over 21 times cosine of pi over 21 x squared minus y squared times, and then I'm left with x cosine theta minus y sine theta, like that. And then of course if you're doing this, partial of g with respect to r, everything needs to be eventually put into r and theta form. Okay? So I've got 2 pi over 21 cosine of pi over 21 x squared minus y squared. That's going to be r squared times cosine squared minus sine squared, like this. Now notice what I did was I factored out the r squared there because x and y both have r in them and they got squared, but I just factored it out, right? So cosine squared minus sine squared. And then right here times x is r cosine theta, y is r sine theta. So I'm going to have r cosine squared theta minus r sine squared theta, because it'll be cosine times cosine, sine times sine there. Let's see. Let's clean this up just a little bit. Cosine squared minus sine squared, I hope you recognize that as cosine 2 theta. Okay? So my partial of g with respect to r is equal to, I'm going to factor the r out here. So I'll have 2 pi r over 21. Cosine squared minus sine squared is cosine 2 theta times cosine of pi r squared over 21 cosine 2 theta. Okay? So that's my partial of g with respect to r. let's make a little space over here and do the partial of g with respect to theta. Okay? So my partial of g with respect to theta is going to be the partial of g with respect to x times the partial of x with respect to theta plus the partial of g with respect to y times the partial of y with respect to theta. Okay? So, let's set it up. The partial of g with respect to x and the partial of g with respect to y, those are going to be those same objects, right? The only thing that's going to change here is the partial of x with respect to theta and the partial of y with respect to theta. Okay? So here we go. I've got 2x pi over 21 cosine pi over 21 x squared minus y squared times, there's partial of g with respect to x. Now partial of x with respect to theta, right? That's going to be times negative r sine theta. Because the r is along for the ride and the derivative of cosine theta is negative sine theta. Plus, now I've got negative 2y pi over 21 cosine pi over 21 x squared minus y squared times the derivative of y with respect to theta, right? Partial of y with respect to theta is just going to be r cosine theta. All right. So let's start cleaning this one up. Let's see what they have in common here. I've got the 2 pi over 21 from each one. They also both have an r, right? So I've got 2 pi r right there. And then I also have these cosines here, right? So cosine pi over 21 x squared minus y squared times I've got what am I left with? I have x with a negative sign here, so I've got negative x sine theta and a negative y also, right? Cosine theta minus y cosine theta, like that. All right. So then from here, I can plug in all of my pieces and start pulling out some more. I've got the 2 pi r over 21 cosine of pi over 21. And then this is going to be like we did before, right? That's going to be the r squared cosine squared theta minus sine squared theta times x is r cosine theta. So I have minus r cosine theta sine theta from this piece minus y is r sine theta, and then I have cosine theta like that, right? Okay, I hope you're noticing something. I can factor out a negative r here, pull it to the front, and what I'm going to be left with is a negative 2 pi r squared over 21. I can do the same conversion here as I did before with the cosine squared minus sine squared. And this is going to add up to, because I've got two of the same thing. Notice cosine theta, sine theta, cosine theta. I factored out the negative r. This is going to be 2 cosine theta, sine theta, because there's two of them, right? They're just adding up. So that leaves me with sine 2 theta. That's this times cosine of pi r squared over 21 and cosine 2 theta. Okay? So I've got my partial of g with respect to theta and my partial of g with respect to r now. Okay? Notice how it does kind of have a nice cool pattern to it, right? With the sine 2 theta and the cosine 2 theta on each one. So what have we actually calculated here, right? What we've done is we've taken a function in rectangular form and we've been able to talk about how changing a polar variable will affect g while keeping all other things constant. So you'll be on the surface of g, right? And then you'll ask yourself, well, what happens if I move radially, just outward, right? What will happen to the value of g? And this is that calculation, right? Or if I'm on the surface of g and I want to move in a theta angular direction around the surface, how would that change the height, the z value of g from the point that I'm at, right? And I have that particular calculation. Okay? Another nice thing that this chain rule gives to us is a quicker version of being able to do derivatives implicitly. First, I want to show you the old school implicit redone in this new format. And in the next scene, you'll see a way that we can use implicit to get to some of our multivariable functions as well. Okay, so remember, old school two-dimensional implicit differentiation was all about finding dy dx when y's and x's were scattered all throughout an equation on both sides, right? So you can have them pretty much anywhere. Something like this yuck monster nasty right here that we're going to be doing. Okay? So here's the chain rule written sort of in a concise form. If I've got some function, capital F, of x and y, the derivative of z with respect to t, basically df dt also, right, is going to be the partial of f with respect to x times dx dt plus partial of f with respect to y times dy dt. Okay, so I just wrote it with a few different terminologies. Now to make this 2D, imagine I just pick a level curve on the surface, right? Make a slice. So I just get one trace out of the surface, which is just going to be a curve, right? In 2D plane. So if I pick a level curve, z is some value. Very typically what we'll pick is z is equal to 0, okay? Then I'll have the function equal to some number, okay? Typically function equal to 0. All right, and then for what we're doing here, you could just let t, the generic variable, be x. So then what I would be doing is the derivative with respect to x, but z is now a constant, right? 0 most of the time, which is going to give us a 0 there anyway. Dx is just 1, and my partial of f with respect to x is still there. My partial of f with respect to y is still there, and dy dx is still there. Okay? But now just solve for dy dx. Notice I'll just subtract and divide. I get the partial of f with respect to x divided by the partial of f with respect to y with a negative sign in front is going to be equal to this dy dx derivative. Okay? So to use this to my advantage, basically what I'll do is I'll take something like this and I'll shove it all to one side to turn it into this format right here, where some function of both x and y is there, right? Some expression in x and y. And it'll be equal to some number. And it can be equal to any number. 0 is very typical, but it doesn't have to be 0, okay? For example, in this case, what I would do is I would start by moving that over. Right? I would subtract y squared from both sides. And now what I've got is this thing right here is my f of xy. Okay? So then this piece right here, f of xy is equal to some number. And again, it doesn't matter what number it is. Typically we pick 0, but in this case I didn't have to. The 2's just an extra number anyway, right? When I do the derivative, it's going to go to 0 no matter which way you take it. Okay, so here, now I can immediately on this guy get to dy dx. Notice that I'm going to do the partial of f with respect to x on top. So the partial of this with respect to x, let me throw my negative sign in. Well, the only x is right here, right? The derivative of this piece is 0. And then the y is along for the ride. So I have y, and then it'll be cosine. Leave the inside alone, right? And then derivative of the inside, derivative of x is 1 times y. So I'll get y squared because it'll be y times y. Then in the bottom, I'll do the partial of f with respect to y of this thing, right? Okay, so an easy part on the end there, I'm going to have a minus 2y. We'll get that out of the way. Here, this is going to be a product rule with a chain inside of it. So derivative of the y goes first. He'll get his turn. It'll just be sine xy. Yeah? Next, leave the y alone, so plus y. Derivative of this is going to be cosine. Leave the inside alone, right? And then derivative of the y is 1 times x is x. Typically what we would do is put the x here next to the y, but this will do just fine, right? I'll just put a couple of multiplication signs here to make it fine. So notice, even though this was not something in 3 dimensions, putting it into an expression of the x's and y's, I can use my knowledge of partial derivatives to easily get to a dy dx. Whereas here's the old school way of doing it. I would have started with this, and I would have done my derivative of x to both sides. This would have been a product with a product inside of it, because I'd have to be doing the derivatives of this simultaneously. So notice I've got my derivative here with a product rule, then plus, leave the y alone, and then the chain part of it is also a product. Yuck. And then, of course, the derivative over here is just the 2y times the dy dx. And that's another thing, the dy dx is I have to worry about sprinkling them everywhere. Okay? And then, of course, you then go about distributing this out, getting all of my dy dx's to one side and the other ones that don't not, and then divide it out. And notice I do actually get the same answer. Of course, right? So not only are the derivatives more straightforward and easy in this structured format, but it's a formula. You can just crank it out instead of having to do a bunch of the solving, okay? So knowing partial derivatives is also going to enhance your 2D game, if you will, right? I can easily do implicit differentiation this way, okay? So what about implicit differentiation in multivariable situations? It's actually very, very similar now that we have these nice formats. Let's go through the chain rule first. Remember, we had the partial of a function with respect to x, but it had multiple variable possibilities. So I've thrown w in there because remember, w is typically what we use as a fourth variable. W would equal f of x, y, z, right? But we don't have to actually let w be a function. What we can do is take a level surface, like earlier, remember we were doing level curves. If we take a level surface, then we get a singular surface, which could be some 3D surface that I'm actually interested in, and treat it the same way to get some implicit differentiation. So this is technically a 4-dimensional chain rule here. W is something based on a function of x, y, and z, which is why you would get the chain rule with the partial of x dx dx, partial of y, dy dx, partial of z, dz dx, right? But notice the same logic as before. If I pick a level surface, basically w is a, right? So you can pick your expression in x, y, and z equal to some number. Doesn't matter what number, okay? And when you do that derivative, that side of the chain rule is going to be 0, okay? And let's say I pick x, for example. It doesn't have to be x. It could also be y, okay? So, of course, dx dx is 1. And here's the kicker. The partial of y with respect to x is 0. Think about the definition of the partial derivative with respect to x. Y is also the other independent variable, and by definition should be held constant because I'm doing the partial with respect to x. So that piece is 0. Okay, so that whole chunk is gone. I just have the partial derivative of f with respect to x and the partial derivative of f with respect to z, dz dx. Partial of z with respect to x, of course, right? And that's actually what we're trying to get at here. Imagine I've got some messy yuck function that I don't feel like solving for z, but I can write it as some expression in x, y, and z equal to some number. That essentially like this, right? This is a hyperboloid of one sheet, right? Because I have the negative 2z squared there. Okay, so then what I can do is, instead of solving for z, I can actually get my partial derivatives this way, and it'd be much faster. It's technically implicit, just like before. I have my x, y's, and z's and all different variety of functions. Now, of course, this one I could get away with solving for z and just having some messy derivatives to deal with. But why do that if I've got a nice, quick way of doing implicit derivatives? I want you to note that these are partial derivatives, whereas in the last scene they were normal derivatives because it was just 2D, right? But it's still the same formula. The negative partial of the expression with respect to x, partial with that expression with respect to z, right? And it's dz dx, partial of z with respect to x. So you can get that same type of formula with the same logic, swapping around if I want to do the partial with respect to y. Okay, so look right here. I've got the hyperboloid of one sheet here, and I want to do some partial derivatives, but I don't want to have to solve for z. Okay, so what I do is I have to set it up as an expression with x, y's, and z's equal to some number, which is technically a level surface of some higher dimensional function, which I'm not really going to care about because I really just care about this one surface. Okay, so here I go. I have x squared plus 4y squared minus 2z squared is equal to 1. Okay, so right here, this expression right here, this is my capital F right here. That's f of x, y, and z, right there. Okay? So then, for my function, for my one surface, if I want to do the partial of z with respect to x, then I'm just going to follow this formula right here. I'm going to look at my expression in x, y, and z. I'm going to do the negative partial with respect to x, which in this case is just 2x, divided by the partial with respect to z, which in this case is negative 4z, right? I can reduce, of course. Partial of z with respect to x is then just going to be x over 2z. And at this point, you can choose to either leave it in terms of x and z, or if you wanted to then solve for z and then come back and plug that in, you could have something that's a function of x and y. It just depends on which way you want to approach your derivative here. If you have coordinates of points, then of course it's very easy to just have the x and the z. All right, partial of z here with respect to y, same idea, right? Negative partial with respect to y is 8y divided by the negative 4z, which of course I can simplify yet again to be 2y over z, right? So definitely for some of these surfaces that we run into that are not already in function format, a much quicker way of getting my partial derivatives ready to go. Now what about something like this, right? Something that I have absolutely no hope of ever solving for z. That's a lot like why we did implicit differentiation back in Calc 1 to begin with. There are going to be some of these shapes. Is this actually a function where z is a function of x and y? Probably not. But it still represents a surface in some way. And when I'm on that surface, I may want to have a partial of how z changes with respect to just x, a partial of how z changes with just y. And again, I've got these nice quick formulas that can help me get there. Okay? So first and foremost, I need to have some expression of x, y, and z equal to a number, right? So in this case right here, I would subtract this over, and really this is what you would get, right? I know I cheated a little bit there because I'm on a marker board. Okay, so I just subtracted that piece to the left-hand side. And now this expression right here is my capital F of x, y, and z. So if I want my partial of z with respect to x, I will just take the negative, and then I've got the partial with respect to x in here somewhere. Well, it's just here. So this piece goes to 0, and then the derivative of one of these is just going to be 4e to the 4x, and of course the cosine 5z is along for the ride. And then I just need to do the partial with respect to z. Okay, so in this case that would just be 6yz minus e to the 4x. So derivative of cosine is going to be plus, let me rewrite this, 5 e to the 4x sine 5z, right? It was subtraction, right? But the derivative of the cosine gave me negative sine, and the chain rule on the inside gave me the 5. So there's my partial of z with respect to x, right? Pretty quickly. And of course, again, it's dependent on x, y, and z, but that's okay, right? There was no way I was going to solve for z anyway. The partial of z with respect to y, very similar, right? It's going to have a negative sign. The denominator is going to be the same. 6yz plus 5e to the 4x sine 5z. And then the partial with respect to y only, right here, right? That's just going to be 3z squared. Okay? So I hope this has, even though it's been a little bit off on a tangent, pun intended again, I hope this has helped you get a little bit further in your understanding of partial derivatives and how they relate to the multivariable surfaces, curves, and beyond type of objects that we're dealing with.